Okay, welcome back. Time for some more notes, this time on velocity equations. So very similar to vector equations of a line. So have a look at that formula. And then here is the velocity equation. So it's basically the same thing, but specifically for when we're talking about how fast something is moving and in what direction it's moving. So velocity has two things that go into velocity: speed, which we're used to talking about, and direction. So when you talk about the velocity of an object, you're going to be talking about not only how fast it's going, but in what direction is it going. So that's why we use vectors, because vectors can give us the direction, and then the magnitude of the vector gives us the speed, how fast it's going. Okay, so this kind of looks like what we had before. So r sub 0, let's start right there, is the position vector at time equals 0. That's why there's a little o right here. So it's very similar to the a in our vector equation of a line. Okay, so let's write that down. So this guy right here is the position vector at time 0, at t equals 0, and t is time. Okay, that's time. So when time is 0, I gotta go close my door real quick. My son is very loud in the other room. Sorry about that. All right, I'm back. Okay. So this is its starting position, and it's very similar to the vector a in the vector equation. Okay, so similar. All right, it's position vector at time 0. So basically where your object is starting. Okay, so starting position. All right, the next thing that is different is this v. We have a vector v. So vector v, this vector is the velocity vector. Okay, it tells you how fast you are moving and in what direction. Okay, it's similar to the direction vector b in the vector equation. Okay, so it's telling you which way you're going, but it's also telling you how fast you are going. Okay, I was just thinking of something else I wanted to say about the velocity vector, but it has now slipped my mind. Oh yeah, so if your velocity is like you're heading straight east, okay, then it's like your speed and your velocity are the same thing, pretty much, okay, because it's going in, your direction is like just that way. But if you start going on a diagonal, then you're going to break down your speed into, well, how fast are you going east and how fast are you going north? Okay, so we're going to break that into two components. We're going to take your speed, your east going speed and your north going speed, and figure out how big those are, and that's going to be your velocity vector. Okay, so if you're just heading east, then your velocity and your speed are one and the same. Or if you're just going north, then your speed and your velocity are going to be one and the same. But if you're going on a diagonal, then you need to, what you're going to be figuring out is basically how fast are you going east and how fast are you going north. You're going to break that into two components, hence the vector. And if you're like an airplane and you're in three-dimensional space, then of course we can throw in a third dimension to that as well. All right, back to what else is in my equation. So the other thing is t. We've talked about t before. Specifically, in a velocity equation, t is always time. T is time. Okay. So, and then r, this puppy here, is the position vector of a point on the line at time t. Okay, so it's where you end up. Okay, so this is the position vector, because it's a vector, at time t. Okay, so basically you can think of it as where you end up. After a given amount of time. That was weird. My screen just did something strange. So hopefully I'm still recording. Okay. All right. If you take the magnitude of the velocity vector, that will give you speed. Okay. So the magnitude of the velocity vector, if you take the magnitude of that, that gets you the speed. So like miles per hour, kilometers per hour, meters per second. Okay. So this is the magnitude of the velocity vector. So remember, velocity is telling you two things, not only how fast you're going, but in what direction you're going. Whereas speed just tells you how fast you're going, doesn't tell you what direction. Okay, now if you know the speed and the direction, okay, so let's say you know you're going, 60 miles per hour northwest. We can then find the velocity vector. Okay, we've got a little formula for that. Notice if you look at the formula packet, these formulas are not in here. There's nothing about velocity on this formula packet. So these are kind of the things you kind of just need to make sense out of. And I know that's going to be tough, but we're going to do our best. Okay, so if you know the speed and direction vector and the direction, of an object, you can find the velocity vector. Okay, because you might not be given, everything you need to fill in this equation up here. You might not be given everything all at once. You might be told the speed and the direction, and then you need to put those together to get the velocity vector so that you can then make your velocity equation. Okay, so there is a formula that looks a little bit different in the book, but this is how I was going to write it because I think it makes more sense to me. So direction vector, the direction, okay, is going to be our direction vector. We need a direction. We need to know like the X component, the Y component, and if we're in three-dimensional space, even the Z component. So the direction is going to be given in a vector form, direction vector, okay? And we usually call that B when we're talking about the equation of a line. We talk about the direction vector as being vector B, right? So if we know the direction, we have the X component and the Y component, and we know the speed, then we can figure out the velocity vector. And the way we're going to figure out the velocity vector is going to be equal to, you're going to take the speed, you're going to divide that by the magnitude of the direction and multiply that by vector B, okay? And I'm going to give you an example and try and make this make sense, okay? Oops, gosh, I keep falling off the bottom of my page there, okay? So the velocity vector is you take your speed, you divide by the magnitude of the velocity vector, and then times by the velocity vector. So I'm going to give you an example of this, and hopefully it'll make a little bit more sense once we do that. Okay, so I'm going to walk you through this. Okay, so let's do an example. We're going to have a boat, because boats can move like any way they want in X, Y directions. Okay, cars they tend to be stuck on streets, so they tend only to go in quite like a little bit more simplistic. So if we have a boat, we're going to have an example with a boat. Okay, a boat is traveling with a speed of 4 meters per second. In the direction I'm going to give you 3I plus 4J. Okay, so every 3 units to the right, they're going to go 4 units up. So that is the same as a direction vector. So find the velocity vector. So I know how fast it's going, and I know the general direction that it's going. Okay, this is a direction vector. It's just telling me that's basically it's parallel to the velocity vector. So it's basically like knowing the slope of a line, but not knowing its y-intercept. It's kind of what's going on here. Okay, so I'm going to use my little formula. The velocity vector is going to be equal to speed divided by the magnitude times the vector. All right, so let's go ahead and fill this in. So my velocity vector is going to be equal to my speed. My speed is 4 meters per second divided by the absolute value of my position vector. So my my direction vector, I'm going to call that B, right? B is equal to 3, 4, if I change that to component form. So therefore, the magnitude is equal to the square root of 3 squared plus 4 squared. Oh, hopefully you recognize that. That's Pythagorean triple. So I could do it on my calculator, but I know that that's just going to be equal to 5. It's a 3, 4, 5 triangle. Okay, so I'm going to have speed divided by the magnitude of the vector, and then I'm going to times that by the vector itself, which was 3, 4. And that is going to give me my my velocity vector. So 4/5, I can change that to 0.8. And then I'm going to times it by both components. And I'm going to get 2.4 and 3.2. Okay, so what is going on here? I'm going to explain that in a second. But before I do, let's just check. If I have a vector that goes 2.4 in the x direction and 3.2 in the y direction, what's going to be its magnitude? Okay, this is a velocity vector, and I said the magnitude of a velocity vector is the speed. So if I take this now and I take its magnitude, I should get this speed, which is 4. So let me just check it. Okay, so I'm going to check it. I'm going to find the speed. Okay, so that's going to be equal to the square root of 2.4 squared plus 3.2 squared. And if I put that into my handy dandy calculator, I get that equals the square root of 16. Trust me, I did it. And that equals to 4. Oh, bam, it matches. 4 meters per second is my speed. So the speed is equal to 4. Okay, I just checked it. Okay, so why does this little formula work? What is going on here? So let's see if I can explain this at all. Okay, so the vector 3, 4, if I were to just take this vector 3, 4, so I'm going to give myself starting point 3 to the right and 4 up. So here's this vector, this direction vector 3, 4. And it goes 3 this way and it goes 4 that way. And we know by looking at our Pythagorean theorem that this is 5. So this has a magnitude of 5. But I said my boat has a speed of 4. So I want the magnitude here to be equal to 4, not 5. So I don't want this whole magnitude. I want less than this whole magnitude. So what part of this magnitude do I want? I want 4/5 of it. I want 4/5 of it. If I take another color, think of it this way, I want this to only be 4 units long. Right now it says it's 5 units long. I want it to be just like 4 units long. So I want to know what is going to be the y component and what is going to be the x component, because I want it to be 4 units long. I want it to have a magnitude of 4. So what is going to be my x component? What's going to be my y component? Okay, these are similar figures. So similar figures are proportional. So it's going to be, I want 4 out of every 5 units here, okay? The whole thing was 5, but I only want 4 of it. So I want 4/5 of it. So that's why I'm doing 4/5 of I'm going to be doing 4/5 of this vector 3, 4, okay? Which I said is the same thing as 0.8 times 3, 4, which gives me that 2.4 and 3.2. Okay, and you can check that on a calculator. I multiplied them out earlier. So this distance here is 2.4, and this distance is 3.2. That's my velocity vector. So this vector right here, this little green vector, this is my velocity vector. This is how fast my boat is going. It's going 4 meters per second, and it's going in the same direction as the purple vector, but that purple vector doesn't have a speed of 4 meters per second. So then I could figure out how far my boat has gone after a certain number of seconds, because now I have my velocity vector. So my velocity vector can now help me figure out how far I've gone in a given amount of time. Okay, so let's do part 2 to this problem. So I'm going to keep going with this same problem. But I'm going to ask you another question about it. So I'm going to tell you at time 0 where it is, and then I want to write the velocity equation, and then we're going to use the velocity equation. Okay, so this was kind of like part A. Now we're going to do part B. We are going to write the velocity equation. We already have the velocity vector. If at t equals 0 times 0, the boat is at 2, 5. Okay, notice those are coordinates. Those are coordinates. So that is the same as my position vector at time 0. So this is going to be my r sub 0. That's going to be my r sub 0. This right here, I know, is my velocity vector. So now I can write my equation. Okay, so my equation from my formula is going to be, you see this? I'm falling off the bottom again. So r is equal to the starting vector, my position vector, 2, 5. And maybe this is like 2 meters east and 5 meters north of, I don't know, a buoy. Okay, maybe it's near a buoy. It's 2 meters east and 5 meters north of a buoy. Okay, and then it's going to be moving at this is going to be its velocity. So it's going 2.4 meters per second to the east and 3.2 meters per second north. And that's my velocity, okay? So it's breaking down the speed into east-west versus north-south, x direction versus y direction. Okay, so I'm sorry, where am I? I need to plug this in. So remember it went v, where is it? It says the velocity vector and then the time. You can certainly switch them. You can put the time first and then the velocity vector. It doesn't matter. right? Okay, but I'm going to go ahead and do it the way that the formula states, which is the velocity vector, 2.4 and 3.2. There's my velocity vector, and then t. Okay, so now we can use that equation to answer questions. So let's say I want to know, where will the boat be after 20 seconds? Okay, so moving on to part C. Where will the boat be after 20 seconds? Okay, so that's time. And remember, my initial units were meters per second, so I'm okay that I'm in seconds. I don't need to worry about converting my time into some other different unit of time. So where is it going to be? So I'm going to take my equation from the previous part. So I had my starting position, and I have my velocity vector, 2.4, 3.2, and I'm going to multiply it by 20. I'm going to multiply by 20. Okay, having the 20 on this side is this exact same thing as having the 20 on this side. You're just going to multiply both of these by 20 and then add them to this vector right here. Okay, so I have my starting position, and I want to know after 20 seconds, where is my boat going to end up? So I'm going to get, I'm going to multiply this out. So I have 2, 5, and I went ahead and multiplied this ahead of time. 20 times 2.4 is 48. And 20 times 3.2 is 64. And then I'm going to add those together, and I get, I'm going to be at 50, 69. So the position of the boat after 20 seconds, it will now be 50 meters east and 69 meters north. Okay, so it started really close to the buoy, and now I know how far away from the buoy it has gotten after 20 seconds, assuming that it started at a buoy, or that 0, 0 is at a buoy. Okay, so that's how we can use our velocity equation to answer questions about the motions of objects. All right, one other example. So what if they give it to you in kind of more like compass directions? Okay, so here comes the next example. So again, we're going to have a boat. We'll get to airplanes when we want to do 3 dimensions. So right now we're just doing 2 dimensions. A ship on the ocean. Okay, a ship is at 3 kilometers east and 4 kilometers north of a port. 2 hours later, it is at 2 kilometers east and 8 kilometers north. Find the velocity and speed. All right, so we're going to do this by figuring out the velocity vector. Okay, so again, I'm going to use my formula. R equals the starting place plus the velocity vector times t. Okay, what do I know? I don't know the velocity. I don't know the velocity vector, but I do know where it's starting. It's starting at 3 and 4. So r sub 0 is going to be 3, 4. And I know where it's going to end up. It's going to end up at 2 and 8. It's going to end up at 2 and 8. And I know how long it's going to take to get there. It's going to take 2 hours. So t is equal to 2. Okay, so it probably would have made more sense if I had switched these at this point. Okay, so 2 times the velocity vector. Okay, so now I'm going to go ahead and I'm going to write 2 equations. One for my, well, actually, let me write the velocity vector as x and y first, and then I'll write my equations. That'll make more sense. Okay, so the velocity vector, I need to solve for, I'm going to put the 2 on the other side because that just bugs me having 2 on the right-hand side. The velocity vector has an x component and a y component. So now I need to solve for my x and y. Okay, so I'm going to write an equation for the x's, which is 2 is equal to 3 plus 2x. And I'm going to write an equation for my y component. 8 is equal to 4 plus 2y. Okay, so now solving for this is going to be really simple. Minus my 3, I get negative 1 is equal to 2x. So x is equal to negative 1/2. And the other one, sorry, I'm getting off the bottom again. Minus 4, I get 4 is equal to 2y. So I get y is equal to 2. So I don't want to have to turn the page, so I'll just do this. Okay, so I'm going to take this, and therefore my velocity vector is equal to negative 0.5 and 2. And since our units were kilometers and hours, this is going to be kilometers per hour. Kilometers per hour. So you can think of this as we're moving half a kilometer per hour to the west and 2 kilometers to the north every hour. Okay, so it's breaking it down into component parts. So that's my velocity vector. Now, to get the speed, I'm going to take the magnitude of that. So I'm going to take the square root of negative 0.5 squared plus 2 squared, put that into my calculator, which I already did, and I get that the magnitude of that is 2.06 kilometers per hour. That is my speed. Okay, so this was my velocity vector. Choose another color. Velocity vector, which breaks it down into the components, you know, my x direction and my y direction, and then the actual speed, which I get by taking the hypotenuse of that right triangle, which ended up being 2.06 kilometers per hour. All right. Last thing, oh my gosh, finally, the last thing, normalizing a vector, also known as the unit vector. Okay, so we've talked about base components and unit components, I, J, and K, right? Those are unit vectors. They're just 1 unit long in the X, Y, and Z direction. Well, what if I want to have a vector that's 1 unit long? How do I get a vector that's 1 unit long that's not in the X, Y, or Z direction? We call that a unit vector. Sometimes you want to just get a little tiny vector. We call it a unit vector. We also call this normalizing a vector. Normalizing a vector. Okay, so we're used to I, J, and K. Those are our base vectors. They are unit vectors that are in the X, Y, and Z directions. Okay, so they are unit vectors because they're just 1 unit long in the X, Y, and Z directions, right? But what if I have a vector that is on a diagonal and I want it to be 1 unit long? Okay, so like I is equal to 1 unit going that way. J is equal to 1 unit going that way. And Z I would draw, except that I don't have a 3-dimensional piece of paper. I only have a 2-dimensional piece of paper. So that's going to be kind of hard to draw on here. So I'm just going to show you I and J. Okay, but what if I want to draw a vector that's 1 unit long, but it's diagonal? Okay, so let's say I've got a vector like, here's 1 unit, right? I want to take my 1 unit, so I could like take a little measuring piece of paper to measure with. So here is 1 unit. There's 1 unit. And let's say I want to put it at an angle. I want it to be like, maybe I want it to be like this. So I want it to start here and there because it's 1 unit long. So it's 1 unit long. That's a unit vector, but how would I write it? because it's not all the way over 1 and it's not all the way up 1. It's part of the way over 1 and a little bit up 1. So how can I make that into how can I write that vector? I know its magnitude is 1, but how am I going to write its components? What's the x component? What's the y component? Okay, so this I know is going to have a magnitude of 1, but now how am I going to put that in vector form? Okay, so this one right here, this, my I, is equal to 1, 0, right? And my j, that's equal to 0, 1. But what's this going to be equal to? What is this going to be equal to? Okay, so what I'm going to do is I'm going to figure out, well, what direction is it actually going in? And so I decided that it's actually pointing at this point right up here. So I'm going to do it. I'm going to move it over here a little bit so I have a little more space. So I think it's actually pointing at this point right here. This is just for convenience. I decided to make it move in the same direction as the vector 4, 3. Okay, so it's going to be in the same direction. Okay, there's my direction vector. So I'm going in the same direction as that. It's going to have the same slope as this vector over here, okay, where it's going over 4 and up 3. But it's only going to be 1 unit long. It's only going to be 1 unit long. So I need to figure out, well, what's going to be its x component and what's going to be its y component, so I can draw that vector. Okay, so notice if I were to complete this purple triangle here, and I'm going to use a different color. If I were to complete this, I could figure out how long this is. So on the direction vector, if this is 4 and this is 3, hey, look at that Pythagorean triple. Isn't that convenient? This is going to be 5. Okay, but I know that this, my unit vector, it has a length of 1 because by definition, because I want it to be 1 unit long, because that's what I want. I want a unit vector, but it's in the same direction as the vector 4, 3. So it's 1/5 the size of the whole vector. Okay, the whole thing is 5. This is 1. So these are similar triangles. So these sides, the x component and the y component, are also going to be 1/5 of this x component and of this y component. Okay, so I can see that this little triangle is 1/5 the size of the bigger triangle. Okay, so I know that my little triangle here is 1/5 of this direction vector of 4, 3. So if I take 1/5 of 4, 1/5, let me write that as 0.2 so that you realize I'm multiplying it by both of these, because otherwise it looks like I've got a fraction times a fraction. Okay, this is a scalar times a vector. So if I do 0.2 times 4, I'm going to get 0.8. And if 0.2 times 3, I'm going to get 0.6. So that is the actual x component and the y component of my little tiny unit vector. And that's how we normalize a vector or make it what's called a unit vector. Okay, so this has a magnitude of 1. This is going to have a magnitude of 1 because that's the hypotenuse is 1. And this is now a unit vector. Okay, so 0.8, 0.6 is a unit vector. And it's a magnitude. So if I do the magnitude, 0.8 squared plus 0.6 squared. If you do that on your calculator, you will see that you get a magnitude of 1. Okay, so there is a formula for doing this. What did I do? I took my direction vector, okay? And so our direction vector, we like to use the letter B. So I take my direction vector, take my direction vector, and I am going to, here's my direction vector, I'm going to multiply it by 1 over the magnitude of the direction vector. I'm going to multiply it, and that's not dot product, I mean that to be multiplication, 1 over the magnitude of the, oops, I'm off the bottom again, the magnitude of the direction vector. Okay, and then the way you'll see this written in our book is that they'll go, oh, well, 1 times the direction vector is just the direction vector. So it's the direction vector divided by the magnitude of the direction vector. And that gets you, that normalizes a vector, makes it 1 unit long. So if you need a vector that's only 1 unit long, but it's in some bizarre direction, it's not in the direction I or J, oh, and I suppose I could add K onto here. K, I'm not going to draw, but that would be, never mind. I changed my mind. Don't put that on there because these were in 2 dimensions. I didn't do 3 dimensions. But anyway, if we wanted to do 3 dimensions, of course we could. That's the nice thing about vectors is all these rules extend to 3-dimensional vectors as well. So anyway, if you were asked to take a vector and figure out what its unit vector is, what if I only wanted it to be 1 unit long? This is how you do it. And that's it. Finally, I'm done talking. Where's the stop button?